Hi, welcome to another episode from Spiral Physics Education. In this episode we're going to be looking at fields and what they mean in terms of physics. We're going to be looking at gravitational fields and looking at point charges in terms of electric fields and also uniform electric fields. So to get the most out of this, it would be really helpful if you had an understanding of what static charges are and that there are positive and negative charges and that electrons have negative charge and protons have positive charge, and also have an idea about the law of electrostatics. And if you're not unsure about any of those, do check out some more videos on the channel to help you get up to speed on them. So, in terms of physics, what does a field actually mean? Well, it's not this. It's not something with cows and trees and crops in them. In fact, fields in physics mean that there are forces going to be exerted, and fields exert forces. So, if there is an object with a mass, it will exert a gravitational field, and that will then be involved with gravitational forces. Objects with charge produce an electric field, and then that will have electric forces associated with it, and then magnetic objects will produce magnetic fields, and they'll have magnetic forces associated with them. So we're all aware of gravitational fields. It's probably the most common field that you're going to be aware of. So to start off with, we're just going to do a little introduction onto that. So gravitational fields are produced by objects that have mass. So every object that has mass produces a gravitational field, and the larger the mass, the larger and more significant the gravitational field. So we call this gravitational field gravity. So on Earth, the gravitational field, or gravity, is 10 newtons per kilogram. And what that means is that for every kilogram, there is 10 newtons of force produced by that gravitational field. So if we have a look at the Earth from space, it looks like a sphere. So the gravitational field on there looks something like this. It's a radial field, and the arrows represent the direction of the gravitational forces in that field. So if we were to hold an object within that gravitational field, it would move and have a force exerted on it in the same direction as those arrows, i.e. towards the centre of the Earth. And if we let it go, it would move along one of those gravitational field lines. However, if we're a lot closer to the Earth looks a little bit flatter. In fact, much flatter. So when we look very close at the Earth's gravitational field on this level, the Earth's gravitational field is uniform. And what that means is the gravitational field lines, rather than being radial like in the other diagram, they're evenly spaced and parallel. But the arrows still point down towards the ground, and that represents again the direction of the gravitational force on that gravitational field. So if we had an object in there, there is a force acting down on it, its weight, and if we were to release that object, it would then drop to the ground along a gravitational field line. So in terms of gravitational fields, the definition is force per unit mass, and that means that it's measured in newtons per kilogram, so force in newtons and mass in kilograms. And that tells us that gravitational fields exert forces when they have mass, so force per unit mass. And on Earth, the Earth's gravitational field strength, or gravity, is 10 newtons per kilogram. So every kilogram of mass will have a force of 10 newtons exerted on it. So we're a little bit more aware of gravitational fields, but probably less aware of what electric fields are like. And if we compare the two definitions, it might seem to make a little bit more sense to you. So remember that gravitational field strength, or gravity, is the force per unit mass, and that's measured in newtons per kilogram. Now, the definition of electric field strength, well, that's force per unit charge, and that's going to be measured in newtons per coulomb. So the electric fields produce forces on electric charges, whereas gravitational fields produce forces on objects with mass. Okay, so let's have a look at some electric field shapes. And I'm going to start off with a positive charge. This is called a point positive charge. So it's an isolated charge, it's a point, it's positively charged, and we draw in the electric field lines, and they look like this. This is a radial field. Now notice that the arrows are pointing outwards, and they point outwards because they represent the direction of the force if you were to put or place a test charge in that electric field that was positively charged. So here's my test charge, and there's going to be a force on that test charge, and it's going to go in the same direction of the arrows, i.e. away from that positive charge. So those arrows show how the direction of the force on positive charges. And if we let that go, then it's going to move along an electric field. In terms of strength of the electric field, this radial field shows that close to the point charge, the electric field is strong, or stronger, because the electric field lines are closer together. But the further we go away from the point charge, the electric field lines get further apart, and that shows that the electric field gets weaker and weaker as it moves away. So if we then compared what the electric field looks like between a positive and negative charge, they look very similar in terms of the shape. They're both radial, but we've got to look at the arrows. So for the negative point charge, the arrows go inwards because the arrows represent, if you like, what would happen to a test positive charge in this field. So if we look at a test positive charge, they're going to be attracted to each other. So that arrow represents a force on a positive charge in that electric field. So the arrows are drawn in that direction. So positive charge in that electric field would be acting towards that negative charge because opposite charges attract. And it would move like that towards the negative charge. But what would happen if we put a test negative charge in each of these electric fields? So there we have our test negative charge in our positive point electric field. Now remember that the arrows represent the force direction on a test object that would have a positive charge. So the negative one will just be in the opposite direction to those arrows. And remember that we're dealing with opposite charges here, so what we're dealing with there is attraction. And if we were to look at a test negative charge in a negative electric field, or an electric field produced by a negative charge, remember that those arrows represent the force direction on a positive charge, but it's negative, so it's going to be in the opposite direction. Which makes sense because you've got a negative charge and another negative charge, and they're going to repel, so that charge is going to move away from that other negative charge. They're going to be repelled. So we also need to know about how to produce a uniform electric field. So those other ones, they're not uniform, they're radial. Their strength changes because the width or the density of the field lines change. So a uniform electric field is produced by putting two parallel plates together and attaching them to a power supply. And on that power supply, we're going to have the top terminals being positive and the bottom terminals being negative. And that means the top plate, in this occasion, is going to be positive and the bottom plate is going to be negative. And that what we'll find is that a uniform field, electric field, is produced. And we can draw a uniform electric field by having evenly spaced lines that are parallel together. But we've got to add arrows onto them. So if we look at this, which direction, if we were to put a positively charged object in that electric field, which way would it go? Well, a positively charged object would move away from the positive plate and it would move towards the negative plate. In this example, moving downwards. So the arrows on this, they would move downwards. So that's a diagram of a uniform electric field. Now, if we were to fire some charged particles into that electric field, this is how they would move, as best as I could animate them. The negative charges, if there was a mixture of charges, the negative charges would move up in that downward electric field, and the positive charges would move down along in the same direction as that electric field, which makes sense because the upper plate is positively charged. So the upper plate would attract the negative charges, and the upper plate would also repel the negative charges, sorry, the positive charges. Or the bottom plate, if you like, would attract the positive charge and it would repel the negative charge. So they always refer back to the law of electrostatics, but that electric field shows us the direction in which the positive charge forces would act in. So I hope you found that introduction to electric fields useful, and don't forget to subscribe to the channel to find out a little bit more about electric fields and static electricity. Press that button, subscribe, come back, and hopefully be able to improve your understanding of physics and get those grades boosted. I'll see you next time on Spiral Physics Education. Goodbye.